Again, exercise 7A, B, and C, but I'm pretty much going to 7A first. Maybe talk a bit about B, but mainly A, just to get you thinking and then get you to work. Tomorrow, you will have your first half on the test, chapter 11 test, and then we'll continue with B and C, second half of the session. Okay? But here we go. Let's start off with exercise 7A. What is 7A about? They are about power functions. There are three things that you need to know from this exercise. Number one, to visualize. I'm going to write here, visualize power functions. What does that mean? I want you to be able to graph the shape in your head. So if I said, what is x to the power of 3/7 look like? You should be able to tell me. If I said, what is x to the power of negative 2/5? You should be able to tell me. That's what I want you to be able to do. So you have to be able to visualize based on any power function I give you, whether it's negative or not. Okay? So that's the first step. Number two, which you need to be able then to, once you can visualize it, you have to be able to determine domain and range. Yes, I was given it today, so I'm going to have to photocopy it for next session, which is tomorrow. Yeah. So you got visualize power functions.
Same with that last act was a lot of calculus and algebra.
Yep.
Will this upcoming act be a lot of circular functions and additive?
I'll be everything together because this second one has to be the same as the last one. Because remember, you only got 4 pillars. And the first SAC, you didn't learn integration, but you're essentially doing algebra, functions, and calculus. Those are the 3 umbrellas. So within calculus, you happen to have differentiation, and you also happen to have anti-diff. But because you haven't learned anti-diff, so the first SAC didn't have anti-diff in it, but essentially you're doing 3 pillars. Functions, algebra, and calculus. Calculus meaning that you have integration in it as well. So you'll be doing it all. You just need to tick off all 3 pillars. That's what you're trying to do. Okay, and the last SAC would then obviously just be probability. All right. Okay, so you got visualize power functions, domain and range. Third one, odd and even functions. How do you know if they're odd or even or neither? And then finally, strictly increasing and strictly decreasing. That's what I want you to be able to remember or check off today. Okay, so today, those are the 4 things that I want you to be able to tick off and say, yes, I know how to visualize it. If I can visualize it, I can tell you domain and range. If you can tell me domain and range, can you tell me it's odd or even? And you have to do a proof for that. So once you know how to do that, the next question is, how do you determine when it's strictly increase and strictly decrease? What do you have to remember about it? Okay, so I'm just revising what we've done in chapter 1. Now, let's have a look at the first one. It says here, use your calculator to help sketch the graph. Yes, I know if you had a CAS, then everything would be easy, but I want you to look at it and use the skill to determine what you can have, what you can't have. So let's have a look. You got 3 times x to the power of negative 1/4 and then minus 1. What I want you to realize is the minus 1 and the 3 is just a transformation. So you don't really need to know that yet. You just need to know what the shape looks like to begin with. So the question is, what does x to the power of negative 1/4 look like? They ask you to sketch that graph. Now, what's another way of rewriting x to the power of negative 1/4? What's another way of writing it? Luke?
1 over 4 root x.
Yes, you can. So it's 1 over root or 4th root of x. Okay? You can write it like that, or alternatively, you can write it as 1 over x to the power of 1/4. They're all the same. Now, once you write it like that, you should already immediately see 2 conditions. Name me one of them. What's one of the conditions?
Because it's a 1 over x, that means x comes to 0.
Fantastic. You can't have x equal to 0. Anytime you have a fraction, the denominator can never equal to 0. So that's a problem. So when x equals 0, it's undefined. What's the second condition, Naz? Are you going to say that one? Someone else. What's the second condition?
Can't be negative.
Can't be negative. Why? Because it's not square root. fourth root. But fourth root is essentially like square rooting. Fourth root is like saying square root once and square root twice. That's what fourth root is. And in case you didn't understand what I just said, x to the power of a quarter is the same thing as saying x to the power of half to the power of half. Oh my god. I don't know why.
So if you have
X to the power of half all to the power of half. That's like saying square root of a square root. Okay? Because x to the power of half to the power of half, you times the powers. Half times half is a quarter. Okay, so we know if you square root of x, that can only square root negative values. If you square root again, then you're only square rooting positive values. Sorry, you can't have negative values.
so say x is equal to 256.
Yep.
Then y would be like a quarter.
Yep. Something like that.
Oh, a quarter times 3 minus 1.
Yes. That's correct. So the question is, now I've just given you two conditions. You said x cannot be 0, and you said x cannot be negative. So you already know the domain based on that. But what does the shape look like? What is... Jack. What does it look like? It's mass.
It'd be like say when like the chord there's like more so it would be like a truncus but more closer to the
No, because the truncus has both left and right hand side. We just said x cannot be negative. If you draw a truncus, there's a negative side to it, so it can't be right. X-axis can't have negative values.
It would be like half a truncus, where it's only like the positive x value of the truncus.
Perfect. It's more similar to a rectangular hyperbola rather than a truncus, but yes, essentially, remember, how do I know what kind of shape this looks? It's more of like, I don't know what fourth root of x is, right? But I do know that 1 divided by a number, I've got a function for that. It's a rectangular hyperbola. 1 over x just means 1 divided by a number. This is a number. I just don't know what that number is. But when I do 1 divided by a number, what does the shape look like? Your rectangular hyperbola looks like this. That's your rectangular hyperbola. That's when you have y equals 1 over a number. It doesn't matter what you're doing to that number. Okay, we know it's a number. So 1 divided by a number. Now, the problem is with this graph, there's a few issues already. I said there were two conditions. One, you can't have x equal to 0, which is already shown. So x can't equal to 0. That's true. But what else can't x be again? Negative. So that means that bottom half right here, I can't have that. That wouldn't exist because none of this x-axis would have existed. No negative value. So I shouldn't have that. So I should only have this one. This is the shape that you have. Now you can put in the transformations. See, what does the 3 do? It's just a vertical stretch. It's a dilation factor 3 from the x-axis. So it makes it thinner. But it still has the asymptote here, asymptote here. Then the -1 just shifts the graph down by 1.
Isn't that mean it's like a log graph?
No, a log graph is the other way around. This is a log graph.
I mean, like it's similar to a log graph.
No, this one has 2 asymptotes though. This one has an asymptote horizontally, whereas a log graph doesn't have 2 asymptotes. It only has 1.
So how would you look at the horizontal asymptote?
It's more of as like you use limits. So as x approaches infinity, 1 divided by a very large number is really small. So approaching 0. So
0 minus 1.
yes, yes, and that's what I mean by using transformation, saying that it's shifting the graph down by 1.
So would it be actually negative 1 or would it be like
The asymptote is -1 because it can't equal to -1.
Alright.
Because we said it's going to get very small, but we never said it equals 0. Now, if you minus all that by 1, then it only gets as close to -1, but doesn't equal -1. True? Okay? So, part of this session, what I wanted you to be able to do is do what I just did. Using your exponential laws, you can then figure out what it can and what it can't. Then I used what we learned from chapter 1. You had 1 over a number. The only shape you have is a rectangular shape, rectangular hyperbola shape. Then from there, apply your conditions and you can predict what it looks like. So I'll show you. Let's see if I was right. So I'm going to add in, let's add in a page. And we had x to the power of, let's try -1 on 4. So here we go. There you go. That's just the right-hand side, and we were right. It was meant to look like a rectangular hyperbola, but can't have any negative values. And then if you apply the transformations to it, we just said times by 3 should make it thinner. Okay, so it should be thinner. So there we go. But it still stays the same asymptotes. But then as soon as I say minus this whole entire equation by 1, I'm translating it down. So, did I do something wrong there? Oh, because no, it should go down by 1.
Oh, but it's like off the range. It's just because it goes 1 and it's off the graph, but it should be at like 80 or something. It should be over 81.
All right, maybe you're right. All right, let me zoom. Adjust the. Let's go from -10 to, let's say, 200. Let's make it -100 to 100. All right, too hard to see. Yeah, so you can see it's already gone past the x-axis there, so it will go down to -1 region. Yeah, it's just it was further out. If you had to work it out, it'd be further out. Okay. All right, excellent. So that's your visualization of x at -1/4. But then what happens if I give you now x to the power of -1/5? What can you say about that? So that will change the equation to 1 over x to the power of a 5th. What conditions do I have now? 1 over x to the power of a 5th. What conditions? Same one as before, except for something. You can have negative numbers. You can third root. Okay, so if you can cube, you can third root. But when you can cube negative numbers, and it also means you can cube root negative numbers as well. Okay, so cube rooting means that if every odd rooting you can do, 5th root, 7th root, 9th root, you can do odd roots of negative values. So what would you predict the graph to look like if you can now have negative x values? You can't have 0, but you can also have positive values. What kind of graph should you expect? Yeah, it should be all of the rectangular hyperbola. Okay, it might just be slightly different, but the overall shape should follow the same pattern. So watch. I'll change, which I just moved the graph back, and I'm going to change the equation to 5. I'm just going to take away the -1 and take away this. And there you go. You can see that it follows. I'm going to do zoom box and just zoom where I want it to have. So let's just say there. You can see that's your rectangular hyperbola, -1/5. Okay. A better question is then, what happens if I then change this to a 2? What if it was -2/5, which becomes 1 over x to the power of 2/5? What would that look like now?
Isn't that the 5th root of x squared?
5th root of x squared. So I've got x squared and I do 5th root.
And then 1 over that.
Okay, so what does it look like then?
Well,
Because you're right, that does work, but you can also see it another way that helps you visualize, because you already know what x to the power of -1/5 is. How can you use that to your advantage to predict what x to the power of 2/5, -2/5? What do you expect here to what would happen if I put a 2? I only change 1 digit. Phoebe? Very good. This is the current shape. You know that x to the power of -1/5, this is what you know. Now how do you get that 2? Well, I can square it as well. Okay, so I can do this. I can do 1 over, instead of saying x to the power of 2/5, I can say that is the same thing as writing 1 over x to the power of 5th squared. I can do that. See this, why would I do that? Is because when you're multiplying powers, remember, it's 1/5 times 2, which is the same thing as 2/5. X to the power 1/5 I already know. We already did it before. It was like a rectangular hyperbola. Now if I square it, what's the benefit of squaring it? What happens when I square it? Yeah, it will change all the negative values down here, all the y values were negative. You're squaring all those, and now they become positive. So what kind of graph do you expect it to look like now? Truncus. Okay, you put a square in that, and that now becomes a truncus, and I'll show you. We chuck in, I changed this to a 2, and voila. All you're doing is you're taking the same graph, but you're squaring all those values. Now, a better question is, what if I change it to 3? And flip back out again, because you're not squaring them. All the y values are going to stay negative. So if I change it to a 3, it's back to the bottom. What if I chose a number larger than the denominator? So right now it's 5. What if I chose 9? Hands up for truncus. 1. Think about it.
Yes, truncus.
Truncus? 2 truncus? Done, here we go. Why is this the case? Because it's odd. It doesn't matter, I chose 3 before. All I was really doing is this. Essentially, you were just doing this. You were doing x to the power of 1/5. Now you can either, negative 1/5, you can either square it, which means you times it by 2, or you can cube it, which means that all the negative values doesn't matter now. See, this is the y values. When you write y equals to x and negative 1/5, this represents the y values. So you're either doing y squared or you're doing y cubed. And if I put a 9 to it, it's still odd. It still has the negative values. Does that make sense what I'm trying to say? So what I'm trying to do is showing you, whoops, not that graph. This graph here, this is the shape of 1 on 5. Yeah, okay, x to the power of negative 1 on 5. That's the shape. When I do square, all I'm doing is I'm just saying all these points here, I want you to square them. And it just so happens that when you square negatives, they're positive. So that means if I put a 4 in it, it should go up. If I put a 6 in it, it should go up. If I put an 8 in it, it should go up. But if I put an odd number, it doesn't matter. I'm just cubing it, I'm just making it thinner. That's all I'm doing. I'm just saying, take that, cube it. Take that to the power of 9. Take that coordinate to the power of 11. It doesn't matter what number I do. I can do 99 right now. Okay, that's an odd value. And it will just still be the same. See, if I change it to 99, whoops.
99.
Yeah. To 99, it should still be the same. It's the same shape, it's just thinner, because you're taking every y coordinate and you're just doing it to the power of whatever you just put there. That's all you're saying. Okay? So that's what I want you to take out of it. So that means now, if I give you a different base, so I did the one with x to the power of a quarter, I did one with a 1/5. So what happens if I give you a random one now? Let's do negative 6 on 7. What should that look like now? So this is still the same as 1 over x to the power of 6 over 7. What should you expect this graph to look? Truncus. Because x to the power of 1/5 is an odd value. Okay, it can take negative values, so it's going to look like a rectangular hyperbola. That's 1/5. Then 1/3 is still going to be exactly the same. Negative 1/3 is going to be the same. Negative 1 is the same. So you see, all I'm doing is x negative 1, x negative a third, x negative a fifth, x negative a seventh. They all should carry the same shape, because essentially the conditions are still the same. It's 1 over a number, which has a rectangular hyperbola shape. It can have negative values, and it can't have 0. So these shapes here are all going to be like a rectangular hyperbola, but when I put a 6 in there, it's an even power. So now it becomes all even. It's all, you square all the values in the denominator, so it becomes positive. So yes, it is a truncus.
So the denominator is always a hyperbola. When it's even, it is just like half of a hyperbola. And when it has a positive numerator, it's truncus.
Yeah, essentially, yeah.
The top and bottom both even.
All right, good question. What happens? Give me an example.
Like x to the power negative 8 1, 2.
Well, that will become like x to the power of -4. Which is still a good question then. What is 1 over x to the power 4 then? It is a truncus, exactly. So if I just go back, it doesn't even have to be a fraction. See, if I just did -4, truncus. Okay? So that's what I'm trying to say. You've already learned the basic graphs. You just need to learn to analyze them. So you can do now fractions, negative fractions where it's negative. What about now if I change this and I ask you, what if it's not negative? What's x to the power of 2/3 look like then? So in order to do 2/3, you have to know what 1/3 looks like. What's x to the power of a third look like? What's x to the power of 1 over 2 look like? Good. It's like a sideways. Now, in order to do x to the power of 2/3, you have to understand this is the same thing as saying x to the power of a third, and then you're squaring it. The only ones you've learnt so far is x to the power of a half. What's x to the power of half look like? Square root function. So it looks like this. It makes sense that a square root function can only take positive values and you don't have the negative side. So it's just this. But then what happens if I put a third then? See, if a half can't take negatives, then can cube root take negatives? And if it can, then what should the graph look like for a third? Yeah, it'll be like the square root shape, but it's on the bottom. So you can cube root. So you're like cube root of -1 is -1. So it's going down there already. So you should know cube root graphs look like this. It's like an S. It's like an S sort of shape, where it's curving towards the x-axis. Now a better question is, well, what if I put a 2/3 then? If you know x to the power of a third, 2/3.
It's like a bird.
It's like a bird. Yeah. See, squaring it, 2/3 should then look like this. That's what 2/3 looks like. Okay, so I'll show you. I'll do 2/3 for you. We'll try 2/3. So you can do negatives, you can do positives, you can do 2/3. Bam! Looks like a bird. What if I then change this?
Wouldn't I have a multi-spot? You know how like more just like a triangle and the zero part that has like no gradient piece, you can't like work it out because on the left it's going to be like going up, right? It's going to be
Trying to find
it's
the
not
gradient
gradient
at
side.
that point.
Is it on the
Yeah.
left design?
Look, there's no gradient at that point.
Wouldn't there also be a similar thing with that?
No. Oh wait, yes. Yes, at the very
Point.
point at x equals 0, it's not differentiable. Yeah. Because of what you just said, exactly the same thing. Yeah. All right. What about if I switched it around? What about x to the power 3 on 2? Now, before you answer this question, I want you to think about this. You know how I keep breaking up the exponentials? I said you can rewrite this as x to the power of half and then cubing it. Why can't I have x cubed and that? Which one is it? Because if you do x cubed looks like this. And then square rooting it will just make it smaller. But then if you do square root of half, I mean x to the power of half, it looks like this. And cubing it will just make it larger. So which one is it? Which shape?
No,
First one or the second one?
it's the first one because it's more like the second one you can't have negatives.
Very good. Now what theory is that? Opposite. Opposite. Exercise7A. The reason why all the other ones didn't seem to matter because it works. Every other one I chose before had a condition. If you think about it, x cubed, remember composite functions? X cubed is what you're doing to it first. You're cubing the values. Now you can cube a negative. So if I put a -1 there, cube of -1 is -1. But then, you can't square root a -1. All of these will be undefined right now. If you try to square root all these y values, they're undefined. So this graph here is undefined when x is negative, but you didn't put a condition here. So x cubed works, but square rooting an x cubed won't work. Why does it work for this one? Because this one says I can only put positive values. So from here, they're all positive, and can I cube all those values? Yes, I can. I can cube all these y values here. That's why, if you remember from composite functions, they always said range of the function has to be a subset of the domain of the second function. Okay, range of F, subset of domain of G. That's what we're doing here. We're saying this is the range, the y values have to match the second function, which is a cube. Okay, and it does. You can cube it. Whereas this one, it doesn't. The range of x cubed, which is all real values, it doesn't fit in to the domain of the square root function. Domain can only have positive values, but my range, I've got negative values there. So that's why this one doesn't work, and when you type in your calculator, they'll sketch that, because that's defined, and they can't sketch this. So when you're analyzing it, those are things to pay attention to. How do we feel? Visualizing the equation. So I just gave a slight introduction again, or reminder about composite functions. But the aim of that exercise so far was to get you to visualize the graphs by looking at the equations.
Are you trying to make sure it's composite function on that?
Should be.
You say it's instead of B, but it's instead of B.
Yeah, but we did composite functions in chapter 1.
Yeah, but it's like chapter 1 out.
Oh, isn't it? Well, then maybe you're lucky then. Maybe it's not in there. Whatever it says here, then it's whatever's that it's there. Okay?
I think if I didn't use composite functions on the second, just
All right, here we go. So we've ticked off the first dot point. I've got another 3 dot points to kick off. We now can visualize the graphs. You don't need a CAS. You can use a CAS to confirm it. You can now state the domain and state the range, because once you can visualize it, you can tell me whether it's all real values or it's not, right? Then going on to the third point, how do you prove whether it's an odd, even, or neither again? So let's take the first one. I had f of x is equal to x to the power of 2/3, and I know it looks like this. Like a bird, or like a bird shape. I know the domain and range. Range is clearly from 0 to infinity. Domain is all real values. Is this an odd or an even function? How do you prove it? There was only 2 mathematical conditions that you had to use to prove whether it's odd, even, or neither. What were the rules again? What do you use to test? Anyone remember? How do I test if it's odd or even? Or neither? Yes, Leah. Very good. The rule, if you've forgotten, write this down. F of negative x, if you substitute a negative x value, if the equation stays itself, doesn't change, it's still f of x, it's called even. Because essentially, you haven't changed anything. If you sub in a negative x, and it ends up being negative of the function, this would be odd. And if it doesn't fit in either of those criterias, then it is neither. So let's do the first one, let's test that one. So f of x I got. F of x is x to the power of 2/3. What I want to test is negative f of x, which is negative of x to the power of 2/3. Okay? Now, these are the 2 conditions. If I sub a negative x in, and it ends up being this, it's even. If I sub a negative x into the equation and it becomes this, then it's odd. So let's test it. I'm going to sub negative x into the equation. I'm going to sub negative x in, so here we go. F of negative x, I sub it in, and I will get negative x to the power of 2/3. Now, currently, it doesn't look like either of these, but I need to simplify this. Using index laws or exponential laws, how do I simplify this? Negative x to the power of 2/3, how do I simplify it? Yes, you could do that. You could do all to the power of 2 and then cube root of that. You can break it apart. You can write it as negative 1 times x. Oh my god. Times x to the power of 2/3. I don't know why it does that. It's just... Yeah. Okay. You can split it up into its terms, and this you can break it up using index laws. You can write negative 1 to the power of 2/3 times x to the power of 2/3. Your job is to figure out what negative 1 to the power of 2/3 is. Now you can do what Luke said. Negative 1 you can do squaring it first and then cube rooting it. -1 squared gives you +1. +1 cube root is 1. So this whole thing now becomes 1, but 1 times x to the power 2/3 is just x to the power 2/3. So it looks exactly the same as the first one. So this is even.
So it should be like also because if you do -1 to the power of that root would be -1 and -1 to the power 2.
Yep. Yep. Okay. So that's how you prove it's odd or even. Let me think of one. I'll show you a neither example. Let's go to give me some space. A neither example will be something like this. Let's do x squared.
Looks messed up. It's probably not.
Oh, yeah. I can do it like this. I think.
Yeah. Just put it.
Wait, no, not like that. Like this.
What?
Does that work?
Isn't that just the?
Yeah, this one would be neither. So how do you know? This is f of x. True? Now if I sub in f of -x, this would be -x all squared minus -x minus 1. True? This gives you x squared plus x minus 1. Now this equation here does not look the same as the first one, so it's not even. But if it's odd, then it has to be negative of f of x, which should look like negative of x squared plus x plus 1. True? Because I'm timesing them all by negative. But then if I compare these two, they're different. So it's not odd, and it's not even, so it is neither. This is an example of neither. So when you sub -x in, it doesn't look like the original, it doesn't look like the negative of the function, therefore it's neither. Okay? And then we're on to our last point. So you now know how to visualize power functions, you now know how to look at the domain and range, you now know how to prove it's odd or even, and then last step, strictly increasing and decreasing. You had a lot of talk about this, and I went to do my research and it was mixed messages, and then finally VCAR, which I don't agree with it, but that's just how you guys are getting assessed. So what was it again? I gave you a nutshell description. Strictly increasing and strictly decreasing, what do you have to remember? Oh. Say it again? You include the points on both sides. So it doesn't matter. So if I gave you this graph here, let's say it goes like this. Okay? And this was A to B. And I asked you, when is the graph strictly increasing? Now we know that it's increasing from A to B. The question is, do you include A or don't you include A and B? You do. Strictly increasing will always include it. It's when they say increasing, you don't. Okay, so that's in a nutshell. If they say strictly increasing, you include them.
And when it's not, you do one.
Yep. So this is strictly, and if we're just asking for increasing, especially if these are turning points, if A and B are turning points, then it's only from A to B, not inclusive. Okay? That's in a nutshell what Mika wants you to know. Strictly increasing means all turning points are included. Increasing only, turning points aren't included. Okay. And those are your 4 parts to remember too. That's just revising 7A, what you did from chapter 1. But essentially, those are the 4 things I want you to take out. The main part being analyzing functions. Okay, you have to be able to extrapolate. I don't want you to memorize what x to the power 3rd looks like. I don't want you to memorize what x to the power -4 and 5 looks like. I wanted you to be able to analyze it. That's the skill. Okay. Now, just before I let you guys off, one last problem, and then I want you to tell me why. This one. What does that graph look like?
Well,
And then I want you to explain to me what's something that you have to pay attention to if the numerator now is larger than denominator. That does make a difference. So think back, what does x to the power of 1/5 look like? And then why do you think the 9 affects it? See, if I chose 3 on 5, you should be able to tell me that because we did that just now. What happens when I make it 9 on 5? And that was the case with the other one, the one with the negative powers that didn't do anything. This one does.
Oh.
And there's a reason for it, and that's why I want you guys to think about it. It is not a truncus because it's not negative. Another way of thinking about this is x to the power of 1/5 all to the power of 9. What's x to the power of 1/5 look like again? Good, like an S. So it looks like this. Like a big S. Like a very big S, right? But now you take all that to the power of 9. So everything gets skewed up, right? So you would think that the graph looks like this. But why doesn't it look like that? And I want you to just drop down the numbers. Instead of 9, what if I had 6 on 5? What if I had 5 on 5?
It's just like really big.
5 on 5 is linear, so think about it. Right now, the graph is like an S because you are curving towards the x-axis. That's a third, looks closer to the x-axis. Okay? But every time you increase the power, it's getting up, further up and up until it becomes straight. So that's where it doesn't lean to the x-axis at all. So as soon as I do 6 on 5, if it's not leaning to the x-axis, it is now leaning towards the y. That's why, if I change the problem to 15 on 5, what does that shape look like? I mean, yeah, 15 on 5. Cubic, and what does cubic look like? Yeah, and that's when it's tending towards the y-axis. So normally it's tending towards the x-axis, but if you keep increasing it, eventually it's tending towards
y.
Yeah. But where's the equilibrium? When it's a linear line, x to the power. Why didn't that happen with a negative though? See, when I did negative with Zahn before and I said negative 9 on 5, and then I said negative 99 on 5, why didn't that affect it? Because it doesn't have an equilibrium. It doesn't tend to anything. It's just still the same shape. It's 1 over that value. Okay? So, just proving it and showing it to you so you can see. If I change 2/3, sorry, I should change that to a 5. So you can see 3/5 is still like an S.
Yeah.
If I do 1/5, you already know that looks more like an S, tends to the x-axis. But then if I change that to now 6 on 5, actually 7, I'll keep it even, 7 on 5, it tends to the y. So if I change it to 9 now, it tends to closer to the y. Yes, 15 would just be, again, cubic. And that looks like a cubic graph. Okay? But that's just a reminder on those points. Okay? But there you go. That's exercise 7A. And I just want you to visualize that, picture it, draw it. That's 7A.